again in this lecture we will continue the discussion of the solution of the one dimensional heat equation. In the previous class we derived the Fourier Poisson formula. Let me recall that. U x t is equal to k dot t star g of x, where k is the fundamental solution of the heat operator and this is the convolution operator. So, explicitly written. So, this is for x in R and t positive. So, this one is 4 pi a square t to the minus half integral minus infinity to infinity exponential minus x minus y square divided by 4 a square t gy dy. So, we showed in the previous lecture that U satisfy the one dimensional heat equation, namely ut u sub t equal to a square u x x and satisfies the initial condition in the limiting sense. Okay, so, we also saw smoothing effect of this fundamental solution that makes. So, even though the function g is merely continuous and bounded or even bounded and measurable, for t positive u becomes a C infinity function, and that is because of this heat fundamental solution of the heat operator. It is also called heat kernel, Gaussian. Okay. So, we use these terminologies repeatedly. So, one immediate consequence of this Fourier Poisson formula is that suppose g is a bounded function and bounded by m for all x in R. So, if you look at the Poisson formula, that immediately implies u of x t is also less than or equal to m for all x in R and t bigger than or equal to 0. This is because the reason for this is, as we saw yesterday, this integral of k x minus y t dy is 1 for all x in R and t positive. So, if g is and that is physically meaningful. So, if you for example, a thin rod, if we heat in a bounded fashion, the temperature that evolves in time also remains bounded. So, another interesting consequence. So, for quick reference, suppose we just heat the rod in a small interval, okay, that is the next one. So, locally what happens? So, that also we can see from the Poisson formula. Okay. Suppose G of x, so the initial temperature is 0 if x is less than x naught, and some continuous function, let me call it g 0 x, if x 0 and again 0 if bigger than x naught plus delta x naught. Okay. So, here is the picture. So, we would just want to see how the temperature evolves in time. So, if we just heat the rod in a very small segment, of the rod. So, everywhere it is 0. So, only heating is done in that interval. So, G 0 is continuous. So, if you look at the Poisson Fourier Poisson formula, you see that the solution is given by u x t is 4 pi a square t minus half integral. Now, only non-zero values of g are there in this small interval. So, this is the Fourier Poisson formula reduces to integral over the small interval. So, by mean value theorem of the integral, this can be written as g 0 j exponential x minus j square by 4 a square t. So, t positive. So, if delta x 0 is very small, so even j you can take to be approximately equal to x 0 itself. So, we know, so this is what happens when you heat the rod in a very small interval. So, we need not even bother about the integral. So, approximately this will be the temperature for positive times. So, this is helpful in quickly reading the temperature. Okay. So, another aspect I would like to mention about heat equation is the time irreversibility. So, unlike the wave equation, where the wave equation is not changed if we change the time to from t to t minus t. So, heat equation is not preserved under the transformation t going to minus t. So, physically this means that suppose we are given temperature in a rod, thin rod, at the present time, we cannot predict what was its temperature some time back, okay, and that is even from our daily experience we can say that. Okay. So, this heat equation, so if we change this heat equation changes to, so del u by del t equal to a square del square u by del x square. Under this transformation, this goes to minus del u by del t and sometimes this is referred to as backward heat equation. Okay, now we will move on to some non-uniqueness questions. So, I was telling in the beginning, so we are dealing with characteristic initial value problem. So, there could be non-uniqueness. If you look at the Poisson formula, it is very difficult to prove that is the unique solution, because even while deriving that Fourier Poisson formula, we made several assumptions, but the end formula was neat. So, we could prove that u given by the Fourier Poisson formula satisfy the heat equation with the prescribed initial condition. And again, producing non-uniqueness is not easy in this case. So, it is not just produce two solutions and say there is non-uniqueness. Okay. So, this in many instances even proving non-uniqueness requires lots of analysis, and this is one example where we need to do some work. Okay. So, this example, standard example, it has become standard example, is due to Tikhonov, Russian mathematician, and example is the following. So, so you define a function u x t. So, this is not given by the Poisson formula, remember. So, this now an infinite series, a power series, let me write n equal to 0 to infinity psi k psi n. Psi n t x to the 2n by 2n factorial. So, even to come up with this example, you can see so much work would have gone into that. Okay. So, this is okay. So, this x in R and t positive and 0 if t 0 and x is in R. Okay. So, what is psi n? Okay. Just so, psi n, first of all, definition that it is a derivative. Okay. Psi n t is nothing but the nth derivative of the function psi evaluated at t. Okay. Here is the function psi. So, where psi z, so it is function of a complex variable. So, you can see the difficulty even in producing this example. Z naught 0 and 0 if z is 0, where z belongs to C, the set of complex numbers, and what is t? T is the real part of z. So, if you look at the definition of u, so but for this factor it almost looks like e to the x square. Okay. If you just this 2n factorial here, but it is not. So, something like e to the x square, but this makes it more complicated, that psi n t. So, what Ticknow showed was then u satisfies the heat equation u t equal to u x x. So, a equal to 1 here, a equal to 1, and u is certainly not identically 0. Okay. And since and it is 0 by very definition, and u of x 0 is 0. That is how it is defined. Okay. So, u is a solution of the heat equation with a equal to 1 with 0 initial data, but identically 0 function is also a solution. Zero function is also a solution. Thus, we see there is non-uniqueness in the problem. Okay. So, we have two solutions here, one is not identically 0 and another one is identically 0, both satisfying the same initial condition, namely 0. So, there is non-uniqueness. So, proving that U satisfies the heat equation requires some work, okay, and this will be provided in the notes. Okay. So, we have to essentially estimate psi and t and show that this power series converges, and we can do term by term differentiation both respect to t and x, and then verify that U satisfy the heat equation, and that requires some computations. They are little hard because we have to go to function of complex variable, and this is estimated using the Cauchy formula. So, the details will be provided in the notes. Not that there are no uniqueness results. So, this example certainly tells us to look for some conditions on the solution, so that we have uniqueness in the problem, and one such result I just mentioned here. So, uniqueness result. As I commented in the beginning, so in order to get uniqueness result, we may have to put some additional conditions, and this is one such result. Okay. So, let me state it as a theorem. Again, proof of this theorem is little lengthy, details will be provided in the notes, but for your information and knowledge this is important to be noted. Fix T positive and let U be a continuous function in R cross 0 t. So, function of two variable x and t. So, let me stress it, U of x t, x is in R and t is where is in this interval, such that the functions U sub t. So, that is so it is differentiable with respect to t, the first derivative, and the second derivative with respect to x are also continuous in the same thing. Okay. If the following are satisfied, let me write it in different way, maybe I will continue here itself, and the following are satisfied. So, this is all part of the hypothesis. U t minus a square U x x is less than or equal to 0. So, let me not write again, it is valid in this domain R cross 0 t. U x 0 is g x, and here the additional condition comes. So, in particular we can take the heat equation. So, here with inequality also it is true. So, u x t is less than or equal to m times b x square for some m positive and b non-negative. So, this is the additional condition we require on the function u. Then with all this hypothesis, then u x t is less than or equal to supremum of g of y, y is in R. So, for all x in R and t. So, in the wake of Tikhonov's example, so if you cannot relax such a condition, that is the important thing. So, if you assume that this function has at most exponential growth with a quadratic term, then this holds, and this immediately implies uniqueness. Why? So, let me just show this implies uniqueness. This theorem, this implies uniqueness. Suppose u1 u2 satisfy the same equation u t equal to a square u x x and u x 0 is g x, same initial condition. So, we have to show that u1 equal to u2. So, you are assuming also that they have they are less than or equal to m e to the b x square. So, that is additional thing, because we are going to use the theorem. So, put v is equal to u1 minus u2, and by linearity, that is important. So, v satisfies a square v x x and v x 0 is 0, and because of that assumption, so v also satisfies such a growth condition, maybe with different constants, that does not matter. Okay. There could be b1 and b2, so you can choose smaller or bigger as the case may be. So, then we can apply the theorem to this equation, and that implies for any t positive. So, v x t is less than or equal to supremum of 0, okay, that is 0 for all x in R and any t less than or equal to t for any t positive. So, we can take arbitrarily large, and that implies V is identically 0 or U1 is identically equal to U2. Okay. So, once we have that theorem, uniqueness of the problem easily follows. Okay. So, thus in the class of bounded initial bounded G, let G the function given by Fourier Poisson formula is the only unique solution of the Cauchy problem. Okay. Though to begin with we did not know the function given by Fourier Poisson formula is the unique solution, we certainly knew that it satisfies the Cauchy problem, but uniqueness was not there. With the help of this theorem, now we also get uniqueness of that Fourier Poisson formula. So, there is also just let me mention one more result. So, there is a result due to Wieder. So, you can see this characteristic Cauchy problems pose so many problems. So, one has to work out for example, here regarding the uniqueness of the solution. This one says if the solution of the heat equation, so instead of growth condition here there is sign condition, solution U of the heat equation, any solution heat equation is non-negative. Okay. So, this is the condition Wieder puts, is non-negative, then uniqueness holds. So, if you consider the solutions which are non-negative, then we do have uniqueness. Okay, so much for this uniqueness and non-uniqueness, and in the next class we will be studying one simple case again where uniqueness holds, and that is somewhat easier to prove, that it just uses the ideas of the calculus. So, I will do that, I will do in the next class. So, the details of the Tikhonov example and the proof of the theorem, though it is hard, so they will be provided in the notes. So, you can go through them in leisurely. Thank you.